All right. So our next speaker is David Salac from the University of Buffalo. I think we're getting to the 10th anniversary of when Matt and I did our first preprint that had Let's Show People PetscFE and PetscFD, and now we get to complete the system. So we're going to hear about PetscFD. So thanks, David.
So welcome, everyone. Thank you. So this is actually going to be a little bit in the same flavor of what was just talked about in trying to simplify finite difference operations. I also want to say, just like Boyce, I'm a longtime PETSc user, first-time PETSc meeting attendee. I will say that it's a little bit shorter commute for me. My office is in the building over there, and I live 10 minutes from here. So I get to go home and sleep in my own bed. Okay, so what I want to talk about is some recent work we've done with Matt and a former PhD student, Abhishek, who is now at AMD. And if I remember correctly, he's actually writing code to simulate next-generation CPUs. So that's kind of cool that he's doing that. And about PetscFD. So what I want to do is I want to talk about sort of the motivation, which I'm going to sort of gloss over a lot because I think most people already have that. I want to talk about stencil composition, which is something that most people sort of understand, but we haven't seen any kind of formalization of it. Introduce PetscFD and then some numerical experiments from that. So most people here probably already know why we do this, right? So I want to sort of gloss over this. Right, but the whole point of this is we're trying to solve PDEs numerically, right? Like was mentioned, finite element, finite volume, we're working with finite differences. And the way that I think about this is basically through stencils, right, which is what most people do, right? A stencil is simply a list of nodes surrounding some point, and then you have associated weights, and then when you do that, you get a set of coupled linear equations where you don't know the function, put that into a matrix, invert all this other stuff. Right, so for example, we had an example of this, right? So one thing is that you can take a Laplace operator, basically apply the Laplace operator to itself, and you get the biharmonic operator. Okay, so that's sort of sequential application of a lower order object to get a higher order object. For more sort of PDE-based type things, right, the Cahn-Hilliard equation is sort of a classic example of this, where you have, and we'll come back to this later on, right, you've got some kind of energy terms, interfacial stuff, mobility, and you apply divergence and gradient and all this other stuff. Now what actually drove me to become interested in doing this was sort of surface Cahn-Hilliard type things, where you have a Cahn-Hilliard equation, but now it's restricted to a surface. So instead of a standard Cartesian Laplacian, you've got a surface Laplacian. And one way to solve this is through something called the closest point method, where basically if you assume that everything is constant in the normal direction, and then compose the derivative operations with interpolation operations, you can now solve this surface PDE in Cartesian space on arbitrary interfaces. So I've done stuff like this in the past for solving a stochastic Cahn-Hilliard on various interfaces, and then like stuff like vesicle simulations and things like that, right? But it's the same idea. You have a stencil, you sort of apply the operation multiple times, so you can get the operator that you actually need. Now, the naive way of doing this is basically, right, these are all linear operators, so you can represent all these operations as matrices, and if I want to do a interpolation operation applied to a differentiation operation, compute the matrix for both, do a matrix-matrix product, there's your operator. Problem is obviously, right, if you have really large systems, you would like to have some information about the sparsity before you create that initial matrix. So it would be nice if we could have that stencil before the final matrix is formed and then form the matrix directly from that. So that's sort of the idea behind this. Right, so the whole idea is that we want to implement extend PETSc so that we can solve PDEs using finite difference methods, using this idea of stencil composition to form a final matrix for arbitrary PDEs. Okay, so I just very briefly want to talk about stencil composition, and like I said, most people are probably familiar with this even if they don't really know it. And to kind of give you an example of stencil composition, let's consider a simple one-dimensional grid, and then at an arbitrary point, I'm going to define one stencil as a forward finite difference operation, another stencil as a backward finite difference operation, and then composing is basically plugging in one stencil instead of having it operate on a function, have it operate on a stencil itself. When you do that, you get the standard second order center finite difference approximation for the second derivative. Okay, so most people are probably a little bit familiar with this. Now the thing that we found lacking was we didn't find any kind of proof that if you do this, are you actually getting the order of accuracy that you expect, and are you getting the derivatives that you expect? You would assume so, but we didn't find anything. So Matt, Abhishek, and I finally got this thing published this year, right? But basically there's a paper out there where we take a look at some important mathematical truths. So first of all, it makes sense, right, that the stencil composition is associative. We talk about derivative operation. What? Commutative, sorry. I did this like 10 p.m. on Monday. Which makes sense, right, because these are derivative operations, so dx dy is dy dx and all this other stuff. Same thing that if we have two stencil approximations of order a and b, when you compose them, you should get the derivative order of a plus b. Makes sense. So one thing that we did formally prove is that if we have a stencil with an accuracy order of QA and then another stencil with an accuracy order of QB, then you're guaranteed that when you do the stencil composition, the order of accuracy is going to be the lower of those two, right? So you're not going to degrade that order of accuracy. And in fact, we can actually even go a step further, and we say if the leading order error term for stencil A is TA, if the leading order error term for stencil B is TB, then you're guaranteed that the stencil composition is going to basically have that leading order error of the lower order method if they're different. Or if you compose, let's say, two second order accurate methods, then that leading order error term is going to be the summation of those things. Okay? So a lot of this stuff is intuitive, but there wasn't actually any kind of formal proof of that, so that's out there now. Okay, so now let's talk about PetscFD, and I'm not going to go into the details about the back-end stuff. I sort of want to just talk about some important PETSc functions, like how a user would actually interact with it. I want to briefly talk about mesh refinement, and then we'll talk about stencils. Okay, right, so the whole idea is that we want to introduce a new class in PETSc called PetscFD. So it's going to extend the support in PETSc for finite difference-based discretizations. It interacts with dmplex and dmforest so that you can create matrices on uniform and non-uniform meshes. And one thing I do want to say, not because of this, but because I'm working with Matt on a project for the DOE CREST, I have learned a lot more about the internal workings of dmplex than I had thought I would need to. So when he talks about jargons like cones, stars, transitive closure, I have had to internalize that, right? And if you don't remember, there's a couple of nice little pictures that Matt has in some of those papers, but neither here nor there. And then the idea is that we want to use the concept of stencil composition when we create the matrices beforehand. Right, and the idea is that we want to try to simplify this. We want to try to be able to generate matrices that will then get passed into a KSP, SNES, or whatever in as simple a way as possible for the user so they don't have to worry about all this back-end stuff. That's the idea. And the target meshes that we're doing are going to be Cartesian but non-uniform. All right, so basically dmforest type stuff. All right, so that's the whole idea that we're building on this. Okay, so the idea is that we're going to have a new discretization, PetscFD, which is going to interact with Plex and Forest. I'm going to talk about node labeling. I'm going to skip stencil creation, and then we'll talk about like differentiation, matrices, and all this other stuff from the end. Okay, so create a PetscFD object just like you would for anything else, right? Create an empty one, PetscFD create. Give it the communicator, spits out an empty FD object. Destroy standard PETSc nomenclature. As of right now, this is still a work in progress. Everything is being set up from the options. So we haven't set up the API yet to do this from the command line, but basically everything's going to be set up from the options. Now, set from options, it does 4 basic operations. The first is it creates a DM, and I'll show you how you can do that through the command line or through a YAML. It labels the nodes, and I'll tell you about the 4 different types of nodes that we have. It sets up the adjacency. So this was a design choice that we had where we basically compute the adjacency for every single node beforehand, so that's easier later on. This may or may not be the best option, but this is sort of what we chose to go with. And then finally sets up boundary conditions. Right now, a very limited set of boundary conditions, but that's expandable. Okay, so let's talk about how you actually set up a mesh. So like I mentioned, we use PETSc options, so there's two different ways of doing it. First way is the command line, right? Everyone's familiar with that. Basically put all the options in the command line. The other way is through a YAML file. So you're asking how to do, right? So basically you create a YAML file, PETSc options, insert file YAML, and it'll automatically do that, okay? The YAML file is a preferred way of doing it just because it makes it a lot more readable if you need to take a look at it later on and reproducible. So for example, if I wanted to make a simple mesh that runs from -50 to 50 with a grid spacing of 1/2, in the command line, these are the options. This tells me the boundary conditions for that. The equivalent YAML file looks like that, and then basically, right, all this stuff gets parsed into the options and then it gets all fed in to the creation of the mesh. For various testing purposes, we also created automatic adaptive meshes from the YAML file. So in addition to this, which is basically just makes a basic square, right, box mesh type stuff, you can also adapt it. So in the YAML file, that's given by the keyword adapt. This is followed by the number of refinement levels that you would have, right? So you have your base mesh. How many times are you going to split it in half? We have two different types of refinement mechanisms right now, is that you can refine about a point, and that's what this is doing, right? So it's saying refine about a point. I'm saying I'm going to refine about 3 points, and the 3 points I want to refine by are points 1, 2, and 3 in those locations, okay? So relatively simple. This was basically just so we could do testing. Another option that we have is via shapes. So right now we just have simple shapes, right? Circles, ellipses, rings, and rectangles. So I can create, let's say, one refined mesh about a circle centered at 1/2, 1/2 with a radius of 1/4. And then that fill operator basically says, all right, do I want to just refine around the interface using a signed distance function representation, or do I want to try to fill it, right? So maybe I'm trying to do some kind of PDE in the circle, so using an immersed boundary type of representation for curved domains, which is something I've done in the past too. And then obviously, you're right, you can use multiple shapes, just throw in the YAML file with all the different shapes, and then it'll automatically create it. So one other thing that PetscFD does is that if you have non-periodic boundary conditions, it always refines to the finest level at the boundaries so that all the boundaries are always at the most refined level, okay? Now, label nodes. So one important operation that we have in PetscFD is because we are working on forests, right, quad trees, octrees, and stuff like that, we have to know what types of nodes they are. So we have 4 different types. The nodes are regular, boundary, hanging, and exterior. So regular nodes are basically nodes that have 4 neighbors in 2D, 6 neighbors in 3D. Does not mean that they have to be uniform, just that they exist. Okay, and you can create directly finite difference approximation stencils from that. Boundary nodes are obviously nodes that are at a boundary of the defined domain. Hanging nodes, like point E right there. Hanging nodes are nodes which have at least one missing node in a given direction. So point E has nodes in the south, right, below it, to the right of it, above it. There's no node to the left of it. So when we create our stencils, we have to know that and do something special. I'm talking a little bit about that in a sec. And then exterior nodes are basically all of the nodes that we create outside of the domain so that we can apply boundary conditions. Okay, so they're not in the original mesh. We just use them so that we can create the matrices later on. The adjacency setup is basically what I said, right, is that for every single grid point, vertex point, we basically store every single adjacent node and their distances so we can create stencils easily later on. Right, we store them in a known order, so like +x, -x, +y, -y, distance between nodes. If a node doesn't exist, standard PETSc nomenclature, we label it as -1. All right? And then this is useful later on when we're trying to create these matrices. Right, so lookup structure and stuff like that. Now, boundary conditions, right, we can set up boundary conditions in the YAML file. As of right now, because this is a work in progress, we have 2. We have periodic, really no boundary condition, and homogeneous Neumann. It's easily set up to do the other ones, but these are the ones that we just had for testing purposes. And then the idea is that when we apply the boundary conditions, we basically apply a center finite difference approximation at the boundary, and I'll show you an example in a sec, and then extend nodes outside so that we can create a matrix. All right, so basically we pad it. I'll skip this one. So let's take a look, right? So the simple example that most people would do is, let's say that we have a 1D example with 4 nodes, and we have known boundary conditions at nodes 0 and 3. Right? You discretize the interior nodes as you would normally. You have a ghost cell, -1 and 4. So then you discretize the PDE, or the boundary condition at the boundary cells, right? Rearrange it like you would normally. And then basically that's the resultant matrix. Okay, so that's the idea behind this. Simple enough. Now, for stencils and matrices, the high-level calls that we have for this. Okay, so after you set up PetscFD, there's 3 basic high-level calls that a user would use. Get derivative matrix, get operator matrix, and the get problem matrix. So get derivative matrix basically says, all right, pass in the PetscFD object, and then tell me what derivatives you want in the x, y, and z direction. And don't know what happened right there. And then what it will do is that from the YAML file, it'll automatically create an appropriate matrix, including the boundary conditions that you have specified. And the nice thing about this is that you can do arbitrary and mixed derivatives. Okay, so if I do, let's say, 2, 3, 0, it will create a matrix which will compute the second derivative in the x direction, third derivative in the y direction, 0 derivative in the z direction. Right? And if you have known boundary conditions, it'll return the matrix of appropriate size that'll compute that. And then all the stencil creation, all the compositions, matrix population, modification of stencil weights, right? That's all done internally so that the user doesn't have to worry about that. The next type is an operator matrix. So if instead of trying to specify individual derivatives in each direction, you want an operator, you can pass in either a gradient, right, in the x, y, z direction. So these are the ones coded up right now. Divergence, Laplacian, or curl. And then it'll automatically, again, in the back end, do all this stuff and return, let's say, the Laplacian matrix for the given mesh. If you want to specify it through a YAML file, then that's what the get problem matrix does. So then that looks at the PETSc options, and then again, it does all the stuff automatically in the back end. Right, so it returns boundary condition appropriate stencils specified from the YAML file. And again, 2 different ways. So this is both YAML, right, but you could, let's say, specify biharmonic, bilaplacian by explicitly stating the derivatives that you want. So I could have a 4th derivative in the x direction, 4th derivative, or sorry, mixed derivative in xy, 4th derivative in y. Or I could specify the same thing as a composition of Laplacians, right? They're both going to give you the same thing, okay? Now, one final thing before we move on to some examples, I do want to talk about how we handle hanging nodes. And basically, the way we handle hanging nodes is we use the method from Min and Gabao about second order. It's a second order level set method for non-graded adaptive Cartesian grids. But the idea is that if you have a regular node like R5 over here, right, you can compute a standard finite difference stencil even if the spacing is non-uniform. If you have a hanging node right here like N1, what you do is you find a ghost node at the edge of the adjacent cell, and then you just do an appropriate linear interpolation from the vertices that support that, replace what the coefficient in the finite difference stencil should have been with that, and now you have a stencil of R1, R2, whatever that one is, that one, and then R5, right? So that's the idea behind this. And it's a very systematic way, and then again, transitive closure, star, cone, all this other stuff, right? Use PETSc to find all these things. Okay, so what I would like to do now is take a look at some numerical examples using this, okay? And the first one I want to talk about is just solving this equation, right? Laplacian, simple Laplacian, periodic boundary conditions with an exact equation that looks like this, sort of a standard test problem. And what we're going to do is we're going to take a look at a uniform mesh and then 3 sample meshes This one refined about 4 arbitrary points, right? This one with a sort of coarse one, and then that thing. And then we do get convergence in all these. I need to go talk to Abhishek about why that's not my expected order, but whatever. But right, it basically it works as we would expect, right? We would not expect case 1 to be as good because it's really coarse. Case 3 does get pretty close at much fewer degrees of freedom and stuff like that. The next thing we want to do, and I want to mention, so from this point forward, everything's going to be on uniform meshes. We want to take a look at some more physical examples. So this is all coded up using PetscFD, and one canonical example we're going to be taking a look at is from Phase Field Hub benchmark problem number 8, and that is a homogeneous nucleation problem. And the idea behind this is that in a phase field, this is going to be Allen Kahn. You start with a droplet or some kind of seed at the center of the domain. Based on the properties, there's a critical radius. If the initial radius of the seed is less than the critical radius, then this will shrink. If it's equal to the radius, it should stay constant within numerical errors. And then if it's larger than the critical radius, this will grow. All right? And the equation we use is the, right here's basically the free energy of this. Looks like an Allen Kahn. We have a simple mixing energy. And then this is the actual driving force for solidification at the simulation temperature. All right, so take the variational derivative of that with respect to the phase field variable phi. You get the Allen Kahn equation. Our initial phase field looks like the thermodynamically correct version, which is hyperbolic tangent. And then what we're going to do is we're going to take a look at 3 different initial conditions. At the critical radius, a little bit below it, and a little bit above it. And then you can take a look at that, right? But basically, if you choose a delta f of square root 2 divided by 30, then that critical radius is 5. And then what we do is we compare the energy of our system, that energy integral that I talked about earlier, using PetscFD versus the benchmark information from PF Hub. And then what we see is that when we have a radius slightly below it, first of all 3 match pretty much with, qualitatively they don't match exactly. But we see that the energy of the system basically goes down to 0, which indicates that it disappears. When we're at the critical radius, right, the energy doesn't change because the shape isn't changing. And if we have a slightly larger radius, right, the energy does go down because this is an energy-driven flow. But in this case, it's actually growing, but it doesn't come down to 0. So that's good, we match that. And now what I want to take a look at is another canonical example, which is spinodal decomposition. So spinodal decomposition has a slightly different energy term, but the spinodal decomposition is composed of 2 different components. There's a sort of chemical mixing energy, and then that's an interfacial energy, all right? So the chemical free energy is a simple double well potential. C represents a concentration, for those that aren't familiar. And then C alpha, C beta are basically the preferred concentrations. So in this one, we have preferred concentrations of 30% and 70%. And then what's going to happen is that this is basically going to try to minimize the amount of interface between the 2 different phases. Right, take the variational derivative of that. You get the classic Kahn-Hilliard equation. And then we do 2D and 3D for this, again, using PetscFD. So here's the initial condition, which is sort of a semi-well mixed case. Using periodic boundary conditions, we can track the free energy. And again, right, the free energy goes down. This is energy-driven flow. And if we take a look at snapshots over time, right, what's the shape that minimizes the volume for, that minimizes the interfacial length for a given volume? Well, it's a circle, right, in 2D. So this is at 100,000, right, 10 to the 4, 8.7 times 10 to the 4, it's basically equilibrium. Because of periodic boundary conditions, right, we get the expected 1 circle. We also did a similar version in 3D, right? So this is a 3-dimensional, same idea with the Kahn-Hilliard spinodal decomposition, right? Energy minimization, just like we would expect. In this case, depending on what your initial condition is, you can either get 2 different equilibrium cases, right? You could either get a sphere, or depending on what it is, you can sort of get this stratified thing, right? So this is just sort of the evolution. In this case, it was a stratified type of result. So this is still a work in progress. Fortunately, unfortunately, Abhishek got a job offer before we were able to fully implement everything. So Matt and I were still working on trying to do this. He's doing better and bigger things, right? But there's still some work to be done with this. We still need to implement, obviously, some additional boundary conditions for this, right? Everything's not homogeneous Neumann, as much as we want it to be. But we're working our way towards it, and hopefully in the near future, we'll be able to actually start working towards merging PetscFD back in. From a personal point of view, I would also like to implement some of the surface PDE things, so start introducing interpolation operations, just because that's what I'm interested in for my research, right, solving surface PDEs, but we'll sort of handle that a little bit later on. But other than that, thank you. And if there's any questions. Oh.
David.
Hopefully this one's quick. So in the initial ghost filling scheme that you showed.
The initial what?
Like ghost filling scheme, or I guess you drew this like non-symmetric stencil, right?
Yeah.
Is that positive definite?
I'm trying to remember if it was actually proven it's positive definite or not. I don't think it is. I have to double check.
Yeah, I don't remember us proving that. We were mostly focused on what's the order of accuracy and.
So the original, I'd have to go take a look at whether Min and Gabao actually took a look at that. I'm not sure.
So that would be a stability proof.
Yeah.
Which you could probably do by going to Fourier, just like all the Strick-Weirda things, right? But we didn't do that. Yeah.
But I mean, that is something that we should probably do at some point.
I mean, so I guess for your max schemes, you've worked out something that you said gives you SPD in terms of computing the Laplacian or I guess, for which operator did you?
This is the Laplacian.
Laplacian, okay.
Yeah, that's done with like, so I think what you did is not equivalent to finite elements, but in a sense I don't know if the phrase Galerkin differences means anything to you. We're basically just using these strange finite element schemes to get SPD operators. Because finite elements are usually SPD.
So we should look in the Gibbon paper because I think they do a stability proof.
Yeah, I'm trying to remember. It's been a while.
But we'll look it up.
Well, I feel like at the end, you can turn anything into a finite difference if you try hard enough. So maybe there's a way to take the Galerkin difference thing and see if it corresponds to any kind of stencil.
Oh, they absolutely do. That's like the whole point.
Okay, well, there you go. So maybe there's some chance for connection between you. More questions? Oscar, questions?
Yeah, I do have a question. Or you go first. Yeah, so very nice work. Really excited to see this automated framework. My question is, does this support block center finite differences?
Block.
So it's just centered at the vertices, but centered at the cells or at the...
Exactly, yeah, correct.
I mean, so what we have implemented does not. I do not see why that would be an issue because, again, at the end of the day, it's just a
You could just take
stencil.
the dual. I think what I would do, if I wanted something that you were writing, I would just take the dual of it because any of the matrices that we're talking about are self-dual. You know, the dual of one of these 2D or 3D is also a 2D or 3D hypercubic, right? It's not true of unstructured stuff. So when you take the dual, you get polyhedral crud, but it's not going to happen here.
Yeah, because everything here has to be structured.
Yeah, that's
right. Because I'm pretty sure.
DMSTAG works because it only operates on meshes and duals where you are, it's closed. It's going back to the same space of meshes.
But when you do this on a forest mesh, you're going to get some non-hypercubic shapes at coarse-fine interfaces.
Oh, that's if you refine before you dualize.
Oh, so if you enforce like a condition on the mesh that you always have refined extra one level beyond. Okay.
Yeah, I totally agree with you that if you dualize after you have hanging stuff, then you have to do something. But probably you didn't want to refine that way for that kind of discretization. Yeah.
Okay.
Blaze, did you have a question?
Yeah, so how much flexibility in defining new complicated finite difference stencils? For instance, all your nice Cartesian product-based stencils, they're nice for smooth functions. But if you want to do something like total variation, you need these really complicated, very wide stencils.
So I think we're fine.
Yeah, I think we're fine there.
I
But
think
so as a user, can I define a new stencil, or do I have to rely on that stencil to be added to PETSc?
So right now, you have to rely on the stencils that we have put in there. Well, so
put one in like we did. So, okay, it's the typical PETSc answer. If you just look at the code, then no problem.
now, let me say this as someone who started off as a user. What I would recommend is maybe putting a hook in there so that you can define your own stencil and you don't actually have to go into the code.
But we can tell you how they're represented. So
Yeah.
stencils are represented as just lists of coefficients with a stencil.
Yeah, it's just node IDs and weights.
And so, yeah, we can throw any list like that in there and turn the crank, and okay, so what can go wrong? You could throw something that's inconsistent. You could try to take the product of two stencils that is weird.
Why would that be? I mean, you may get the wrong answer, but
Yeah, you could do something where you try to step too far out of the domain or something like that. But if it's all interior, I think it's fine. We proved for totally periodic things, the proof says you always give the minimum order of accuracy. So you can't screw up unless you go to a bound.
I think the tricky part is if you try to compose stencils that are not dense.
Even if it's not dense, I think you're okay.
Okay.
It's just if you hit the boundary,
it
all
died at the very end.
we need to do special stuff for that.
And the
Oh.
second comment, how did you manage to solve the Poisson equation if you only have a homogeneous Neumann and periodic boundary conditions?
You use multigrid and you do SVD on those. Of course.
But at some point you have to.
Oh, I mean, no, yeah. So that particular case, right, has a zero mean, so you can basically force it to go to a zero mean.
But it works if you just do multigrid and do SVD on the coarse grid.
Because you,
But you get the zero mean.
You get the zero mean.
You get the zero mean.
you still have solved a problem for which you don't have.
Yeah, I mean, yeah,
Oh,
yeah.
yeah.
You have to worry about the null space and all that other stuff. But
Well, you
just
don't
be
have to prescribe the null space. That's the thing, because the default prolongation operator preserves it. If it didn't preserve constants, then we would be in trouble, and that's why sometimes you have problems with elasticity because it won't preserve the rotational trim models.